Hi everyone. Last time we talked about inscribed angles in circles. An inscribed angle is an angle whose vertex lies on the circle, and the measure of an inscribed angle is equal to half the measure of its intercepted arc. That's the inscribed angle theorem. Today we're going to talk about a couple of different angles in circles that are related to inscribed angles. Now I'm going to grab this point x and I'm going to move it into the circle. What do you think is going to happen to the measure of angle AXB? Well, as x moves in, the measure of that angle increases. One reason, or one way to see that, is to move it to the center. We know that the measure of a central angle is equal to the measure of the intercepted arc. The measure of an inscribed angle is half the measure. So the central angle, which we can get to by moving into the circle, is definitely bigger. If we move the point out of the circle, the angle gets smaller than what it was as an inscribed angle. And we're going to explore how to calculate the measures of these angles, whether the vertex is inside or outside the circle, and it all relies on knowledge of inscribed angles. So let's go with this situation inside the circle first. What I'm going to do is I'm going to extend these sides like that. This is now called the angle formed by two chords. AC is a chord and BD is a chord, and so we're thinking of this as the angle formed by these two chords. Now, there's a nice relationship between the measure of this angle and the measure of these two arcs that are intercepted. So notice that these two angles are congruent, they're vertical angles. And each of them intercepts an arc. This one intercepts arc AB, and this one intercepts arc CD. Now, the measure of this angle, formed by two chords, is the average of this arc and this arc. If this point is outside the circle, then the measure of this angle is equal to half of the difference of these two arcs. So this arc measure minus this arc measure divided by 2. So inside the circle, it's half of the sum, the average, this arc measure plus this arc measure divided by 2. Outside the circle, it's this arc measure minus this arc measure divided by 2. And of course, on the circle, it's exactly half of this. Now, the way you prove these theorems about these various angles, this is the angle formed by uh, two chords. We call this the angle formed by two secants. Recall that a secant is a line that passes through the circle twice. So the way that you calculate or prove these formulas is by using knowledge of inscribed angles. So for example, one thing we could do is we could construct this segment right here. Now notice this angle is inscribed. It's equal to half of this measure. And this angle is inscribed. It's equal to half of this measure. By the exterior angle theorem, this angle is equal to this measure plus this measure, which is half of this arc plus half of this arc. And therefore this is half of the sum of the two arcs. The same idea works outside with the same construction. This intercepts this arc, so this angle is half of this arc. This angle is half of this arc, so because this is exterior to these two, this plus this is this, so this minus this is this angle, which means half of this measure, half of this arc minus half of this arc is equal to this angle right here. So these are the two situations where you have the point inside the circle and outside the circle. This is the angle formed by two chords. It's half the sum of the intercepted arcs. And the angle formed by two secants is half the difference of the intercepted arcs. There's one other interesting situation that arises with tangents. So here is an angle formed by a chord and a tangent. Now, how are we going to figure out how to measure this angle? Well, it turns out that there's a pretty cool way to do it. See this inscribed angle right here that intercepts this arc. Let's construct this angle right there. Notice that the measure of this inscribed angle is equal to, of course, half the measure of this arc. And it appears to be the same as this angle here formed by the tangent and the chord. That's because as we move this point, x, along the circle, this angle doesn't change at all because it continues to intercept this arc AB. And so it's always half the measure of this arc. But notice, as we move x closer and closer and closer, those two angles end up being the same. And so this is like a special situation, a special limiting case of the inscribed angle situation, this angle between a tangent and a chord. And so the angle between a tangent and a chord is also equal to half the intercepted arc, just like the situation with an inscribed angle.